So we're now live in the Autoliv outfitted Mercedes here. It has all types of sensors on it, and we're here with experts Alan and Roxie, and Gary's with me too, and we can do some questions as we go along and record some data. So Alan, can you tell us about this particular car, what sensors it has and how it's outfitted?
Sure. So there are four of Autoliv's 77 gigahertz sensors on this car, one in each corner. On this particular vehicle they're mounted 45 degrees. They're 77 gigahertz and they occupy about 850 megahertz of measurement bandwidth, about 950 megahertz of actual sweep, which makes them very good distance resolution sensors. So the range bins are 17.5 centimeters. That makes it today the highest resolution in distance terms sensor on the market. They're positioned in all four corners. And we see, depending on the field of view, whether on the front and the back, about 105 metres out from the vehicle, and to the rear, instrumented range is about 150 metres. And also, importantly, we see very, very close to the car. Because of the very good distance resolution, we can see right down to the bumper, range bin 0, which allows us to do some very close sensing for side impact and active blind spot features that are supported by the sensors in this car.
So in general, what type of data do you typically collect and how does that feed back into your design process?
Yeah, so we record absolutely everything. Normally a vehicle like this, you notice the LiDAR on the roof. That's used for instrumentation. There are about 5 cameras on this as well. But in terms of the actual radar sensor itself, we record raw ADC data through a measurement interface. That's that roughly 300 to 500 megabits per second per sensor that's running on this live today. Then we also record different parts of how the vehicle behaves. So we record the vehicle dynamics from the CAN interface at the same time, as well as synchronise with all the ground truthing measurement equipment that's on here. That's all recorded in a massive great hard disk in the trunk. And then we take that data and then we use it to play it back through our software development. The intention is to be able to drive once but develop many times based on that recorded data, assuming you don't make a modification to the hardware. So in front of us you can see a normal guardrail view, and there are posts and there's a big flat guardrail. So can you see all these individual dots? Look in front of you, those are each of those individual posts which is holding up the guardrail is one of those individual dots, which is an individual detection that the radar sees from in front of us, and you can map those one to one from what you can see, and that's related to, you can see the car go past. Yep. Again, you can see display from the left sensor in one colour, it's looking that way to our left, and then this sort of reddy pinky colour is the one from the right.
And so you're using the LiDAR in this case for the ground truth?
So this isn't an imaging radar, but you can see that it's not very far away from being one. And again, people use imaging for different things.
Autoliv basically does these types of active safety systems that are integrated into OEM cars. And maybe, Roxie, you can talk a little bit about what's analog devices play in this market.
So analog devices, we're considered a tier 2. So we supply tier 1 such as Autoliv with components to make their radar and LiDAR systems. And so for radar, we're very active with many of our PLL and other technologies, ADCs. And then moving forward, we have an integrated solution, our DigiMimic for 77 gigahertz, that's currently in development.
So what we have is a set of periodically spaced reflectors in a straight line. And as we drive through those, we'll be able to see on the video individual dots on the left and right from each of the sensors, which are these individual mark reflectors that we see. We do those tests in a simple environment to get a baseline for what the sensor's doing, but of course the real world is much more complex than that. And as you saw when we drove past all the parked cars, as we do here, you'll see very, very, very many reflections from each individual point, because there's a belief out there that a vehicle is one object. It's one physical object, but of course it's specular in nature. If you try to draw the vision analogy, it sparkles over time. So depending on how you illuminate it and where you illuminate it from and the orientation of the vehicle, as you illuminate it, different bits of the vehicle appear brighter or less bright. So it sparkles in an electromagnetic sense. And as I said, we get something like 200 detections from each of the radars in here. Remember there are 4, and that happens every 40 milliseconds. So the update rate's 40 milliseconds. So even at the detection level, which is a very, very data compressed part of the radar signal processing chain, the information richness is still very, very high. And that comes back to our fusion question about what is the right level inside that processing chain to do the fusion.
So beyond the data, what's the next level of software processing that takes place?
If we talked about classic radar signal processing, you start from your time domain waveform, which is a sampled signal, and then you have some time of, usually if it's a frequency domain radar, you have some kind of time to frequency conversion, classically an FFT, doesn't have to be. That gives you a range Doppler map, and then from the range Doppler map you would extract a detection list, usually by thresholding is the simple way of doing it. And once you have a detection list, you would then do parameter estimation. So a detection list is just where the thing is in the range Doppler domain. But what you really want to know is not just its, you need to know a more refined version of its distance, not just which bins the object is in, but then also to determine the angular position. We would normally do that after we've done a detection. Just past a rectangular object there, can you see it? This nice square here. Now that's all the individual reflections from that chainmail fence around that object. Sorry, carrying on with the conversation about the processing chain, once you have parameter estimation from a detection list, then that's classically fed into a tracker, and then a tracker is something that has history or memory, and then it would allow you to observe how that object moves over time, and then also to be able to estimate its trajectory, not just its velocity and speed and angle, but what direction is it going in. And that's interesting for autonomy because you need to be able to anticipate to a certain extent what objects are going to do. So if you just know where they are and how fast they're going, it doesn't tell you what they might do. Higher levels of understanding the orientation of the vehicle as well as its trajectory are important. And orientation, I mean by that the stance of the vehicle in the environment around us. Because if you know it's going at a certain speed at a certain angle, it's important to know the where the vehicle's pointing, for example. And that allows systems to make a more informed decision about what that object might do. For me, the real challenges are in the signal processing. The radars we have today generate much more raw data than we actually use in the end because we can't process it all in a cost-effective manner. If you gave me a big enough bill of materials and a very large thing in the trunk, imaging radar I would say is quite plausible today, but you couldn't put it on somebody's affordable vehicle, and that's what the thing is all about here for us anyway, is that if something's not affordable, then I can't put it on the everyday car, then I can't save everyday people's lives, right? That's the critical thing that we fight with. So for us, a lot of it's about the cost of the signal processing, I would say. There are other things, of course, like you have a limited aperture that you can play with, physical size really, what that equates to. And that's why running at higher frequencies is good for us, because then you can maintain the same physical size, but increase the aperture.
And I think another kind of, couple of key areas that we focus in on at Analog Devices is really focusing around some of the core performance specs of the radar as well, around increasing the output power and lowering the phase noise to kind of help enhance the resolution specification that we've been talking about.
Yeah, and I didn't talk about that, but that's absolutely very key as well. We're limited by regulation in some areas, so there's always a maximum output power that we can radiate, but we need to radiate, of course, that as a good engineer over all extremes, all temperatures, under all conditions, so that's often quite a challenge. And then basic sensitivity is always a question. You have to be able to see around you, just being able to see in the front is not good enough, especially for autonomy. And as you said when we talked about the environment, it's also crucial to be very tolerant to bad environments. So being able to see through a bumper fascia, which is not a simple thing at 77 gigahertz or 79, because it is a secondary radome, is pretty key, and there are a lot of very, very advanced algorithms that we develop that allow us to behave in a well-defined way behind the bumper. And of course, when you look at different cars, everybody's bumper's different, and if you talk in electromagnetic terms, then because our wavelength is 3 millimeters at 77, then distance changes of that order of magnitude impact the electromagnetic environment that you're sat in, and 3 millimeters is not very much. So production tolerances and interactions with the bumper, not just the bumper, the bracket, and also not just the bracket, but the metal and the plastic that is around it and behind it all play a role in the clutter that you get back from the world around you.
We've seen the radar sensors at 77 gigahertz with like 1 gigahertz of bandwidth moving to 79 with 4 gigahertz of bandwidth. What challenges do you see there, Roxie, from making them in the component and subsystem level?
That's a great question. So for us, that's no challenge at all. Actually, our new DigiMimic device that's in development right now supports 76 up to 81, so it's actually 5 gigahertz of bandwidth. And so, we don't see that as an issue. We actually see this as an area that we're really excited about in terms of moving forward, in terms of enhancing the performance of radar, as Alan has been talking about.
And I've heard some talk about detecting microdoppler and as far as characterizing different objects? Is that a trend that we're working on?
Yeah, so one of the things that we're really excited about with our DigiMimic device is it does enable microdoppler. So this is a very interesting concept where you can actually detect, for instance, the motion of a pedal, and therefore back in the processing area after, you can detect that, hey, or realize that that is a bicycle by the movement of the pedal, and therefore feed that back into your perception sensor fusion to enable now that, a camera might see that there's a bicyclist, but your radar is going to be able to back that up so that you can in fact confirm that that is in fact a bicyclist.
So both of you are obviously very involved in this technology. How much of it are you actually using in your own personal cars?
I use quite a bit of it. I actually drive a car that has analog devices components in it, so I think it's something, when you work in automotive safety, you are very passionate about what you do, and it shows, I think, in the vehicle that you choose to drive.
So I have a car that has active ADAS systems in it, stereo camera and other sensors. 95% of all fatalities are caused by human errors in vehicle accidents. And a lot of that is by inattention. Classic, right? Me talking to you, I'm not looking where I'm going, small kid runs out in front, fiddling with the controls, which you have to do. And it's very often that, that 300, 400, 500 milliseconds of inattentiveness when something happens and you didn't observe it. And then we spoke about the cycle time of the radar, it's 40 milliseconds. It's much faster, much faster than your reaction time. A good reaction time, I think, for a human being, pilots is 200 to 300 milliseconds. That's if you're being observant. If you're not being observant, it's much longer.
Well, thank you, Alan, for this drive on the Autoliv test track, and Roxie for giving us your perspective. Thanks to everyone who's watching this episode of Frequency Matters, number 100. And we want to thank Analog Devices especially for making this program possible by sponsoring this episode.